He knows a lot about the science stuff. Professor Dave explains.
Okay guys, this practice problem is very straightforward. We have a starting material and we have a sequence of 3 reaction conditions we are going to subject it to, and we just have to look at what these are, recognize what they're going to do, and try to draw the product of this sequence of reactions. So give it a shot. So let's go through these reactions one at a time. What is the first thing we're doing here? So we've got bromine and HV. What is that? That's light. So that's indicating that there's a certain frequency of light that is going to be relevant here. And so while at first we would see Br2, we would think, okay, that's going to react with a pi bond, maybe do a dihalogenation. But in fact, that's not what's going to happen, because although we do have pi bonds here, that's benzene, and an aromatic ring like benzene is not going to do addition with bromine. So instead, we recall that these are the conditions for radical halogenation. So this is a way that we can halogenate at an aliphatic position. We can do this on an alkane. And if we remember something about the regioselectivity of radical halogenation in terms of bromine, radical bromination is highly regioselective, as opposed to radical chlorination, where the chlorine will just end up in a lot of different places. Bromine, when we're brominating, as a radical, the bromine is going to go to the most substituted carbon. So we know that we're going to put a bromine on this molecule and it's going to go there. Okay, we know that that is what's going to happen. So for the first reaction, let's just call this reaction 1, right? We don't need to show the whole involved mechanism. We remember that radical halogenation mechanism from the organic chemistry series. And so we can draw this. And we have this here. This is not going to be stereoselective, but we don't care. So it would also be the enantiomer, but we'll just draw one of these for now. So we know that we're getting a bromine at the most substituted position on the molecule. So bromine is definitely going to go there exclusively. Now for number 2, right? If we're looking at reaction 2, what's going to happen here? Well, we've got methoxide in methanol. Okay, so that's one thing, and we know it's pretty hot. So we've got this alkyl bromide. We've got a strong base. We've got methoxide. So we know that probably SN2 or E2 are going to be likely candidates. But a couple of things. Number 1, it is hot. We know that hot temperatures favor elimination over substitution. Second of all, we can't do substitution there. We cannot do SN2 there. So we know that we're going to do elimination, right? We know we're going to do E2. So we know that that's what's going to happen here. But there are different protons that are available. We could be getting some of the protons here, right? We know that there are some protons here. But there are also protons here that are beta, that are in the correct position there. But what do we know about methoxide? Methoxide is, we need to understand that it's not very sterically hindered, right? Methoxide is not sterically hindered. It has equal access to any of these protons. So it's going to go the thermodynamic route. It's going to want to produce the most thermodynamically favorable product. So it's going to go and get one of these guys. We're going to kick that off that way. So that will give us this here. Okay, so that's going to be our alkene product of this E2 reaction. We're going to get that double bond there and not there. If this had been tert butoxide, then we would have ended up with the double bond here, because we would have to get these more sterically available protons. But methoxide, no problem. And then lastly, for reaction 3, we know that this is going to be a dibromination, right? So whereas before we didn't have any pi bond, apart from the pi bonds in the benzene ring, which are not going to be reacted towards addition reactions, we didn't have any other pi bonds available. So we didn't do dihalogenation, and HV, that tipped us off that we were doing radical bromination. Over here, we see the standard conditions for dihalogenation, right? Br2CCl4, and we do have a pi bond available for an addition reaction. So we can just do regular dihalogenation here. And so that is going to give us a mixture of products, because we can have, right, we can have the bromonium ion intermediate. If we had the bromonium ion intermediate form on the wedge, then the bromide would come in on the dash, or we could do it the other way, and we could have, right, we could put this methyl on the wedge, and this would be as though the bromonium ion intermediate was on the dash, therefore the bromide came from the front and opened that up that way. So that is an anti-addition reaction. Those two bromines have to be trans to one another, and so those are the stereochemical possibilities there. So once again, radical bromination, Zaitsev E2 elimination, and then dihalogenation is going to give us the product of this sequence of reactions. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.